Welcome. In the last lecture, we discussed what is the homomorphism of a group and what is the isomorphism of a group. So we studied what is the homomorphism from the group G to Z dash. So f is a function from G to G dash. Then f of AB is equal to f of A into f of B for all AB belongs to G. Then the function is said to be homomorphism. And we also study the what is the isomorphism of a group. So if the function is homomorphism, the function is 1 1 and the function is on 2, then the function is said to be homomorphism of a group. So what is the theorem here? Theorem. So if G to G dash, function from G to G dash is a homomorphism, then the range of a group G of a group G is a subgroup of G dash. Okay, subgroup of G dash. So what is the theorem here? So f is a function from G to G dash is a homomorphism function. Then the range of this function of a group G is a subgroup of G dash. Okay. So what is the proof here? Proof. Let it. Function from G to G dash is a homomorphism that is given here. From G to G dash. From G to G dash. Okay? From G to G dash. So this is a homomorphism function from G to G dash. So that is given here. So what is the range of the function? Then range of f is defined by so what is the definition of range of function? Is defined by, so what is the f of G? So G, what is the range of G? So there is f of G. So f of G is the set of all elements such f of G where G, small g belongs to group G here. Okay, set G. So this is a definition of a range of a function. So we shall prove that here. We shall prove that f of G is a subgroup of G dash. Okay. So what is the f of G? F of G is the range of function. So f of G is a set of all such f of small g. Then prove that this is the subgroup of G dash. F of G is a subgroup of G dash. So what is proving here? So prove that f of G is a subgroup of G dash. For that, we shall prove that. So if G is a subgroup of G dash, is a subgroup of G dash, then something G is a subgroup of G dash, then how to prove that G is a subgroup? So for AB, so we have to prove here AB inverse belongs to G dash. Where AB belongs to G dash, then G dash, just a minute. So something said AB inverse belongs to G, then G is a subgroup of G. So that is the definition we have to show, see in the previous lecture here. Okay. Since F is a homomorphism, so that is given here. So what is the definition of homomorphism? So that is F of E is equal to, so we see theorem here. So theorem 1, after definition of homomorphism, F of E is equal to E dash, where E belongs to G here and E dash belongs to G dash. E dash belongs to G dash. So this is very simple here. So that is E dash, this implies that E dash belongs to, what happened? E dash belongs to F of G here. Okay. F E dash. So F of E, so this is a range, F of E. So what is the definition? So we take here E. F of E. So F of E, G, instead of G we take E. So that is F of E. So this is element of F of G. So that is F of E is what? E dash. So E dash is the element of F of G. So hence there is at least one element is there in F of G. So F of G is non-empty set. Hence F of G is a non-empty subset of G dash. Okay? So at least one element is there. That is E dash. So first we prove that. So F of G is non-empty. So then we shall now prove that. So F of G is a subgroup of G dash. Now we have to prove in here. F of G is a subgroup of. First we prove that F of G is non-empty. So our next target is prove that F of G is a subgroup of G dash here. Okay, let F of A, F of B are the elements of G dash. Okay? Then what happened? Then F of A into F of B inverse. F of B, its inverse. We take F of A into F of B inverse. So we take, so that we take this. Take this is our choice. F of A into F of B inverse. F of B, its inverse. So by theorem, so F of A as it is. So this can be written as F of B inverse. So we proved this theorem in the previous lecture. So F of B inverse is equal to F of B its inverse. Okay? So this can be written as by theorem here. By theorem. So we are already proving that theorem here. Okay. So what happened here? So F of AB inverse. So F of A into F of B inverse is equal to F of AB inverse. Since F is homomorphism. Okay. So what is the definition of homomorphism? F of AB is equal to F of A into F of B. So this is the definition of homomorphism. And by using that definition, so we write this. F of AB inverse is equal to. So this implies that. So what happened here? So A, B belongs to G implies that G is a group here. A, B belongs to G. G is a group. Then A, B inverse belongs to G. So what is the definition of what is the theorem? So we have to prove all the theorem. If AB belongs to G and AB inverse belongs to G, then G is a group. Then G is a group. Okay, G is a group, so we can write like that. Okay, so this equal to, so this implies that. So what happened here? So this implies that, so AB inverse belongs to G, then F of AB inverse belongs to F of G, no doubt. F of G. So AB inverse belongs to G, then F of AB inverse belongs to F of G. So what happened here? So what is F of AB inverse? F of AB inverse is this. So this is, so this implies that F of AB inverse is this. So F of A into F of B its inverse belongs to f of g. F of g. Okay? Then what happened? Then what happened here? So if A and B belongs to G, then AB inverse belongs to G, since G is a group. G is a group. So f of A into f of B inverse is f of G, then f of G also group. And f of B is a subgroup of G dash. F of G is a subgroup of G dash. Hence f of G is a subgroup of G dash. So this is very simple proof here. Okay. So we prove another theorem here. So take theorem. Let f of function from G to G dash is a homomorphism from a group G, from a group G into G dash, okay, and H is a, and H be a subgroup of G, H be a subgroup of G, then f of H is a subgroup of G dash. Proof. What is the theorem? If f of G to G dash is a homomorphism from a group G into G dash, and H be a subgroup of G, then prove that f of H, so image of H, so f of H is a subgroup of G dash. H is a subgroup of G. So what is the previous theorem? F is a function from G to G dash is a homomorphism. Then the image f of G is a subgroup of G dash. So what is the theorem here? So function f from G to G dash is a homomorphism, and H is a subgroup of G. Then prove that image of H is a subgroup of G dash. Okay. So this theorem is very simple here. So what is this? Look. So f from G to G dash is a homomorphism. So that is given here. So that is from G to G dash here. So that is given here. Also given, what is given? And H be a subgroup of G. So that is given here. Okay. That is given here. So then what is f of H? Then f of H is what? So this is element, set of such element fx where x belongs to G. Okay, x belongs to G. Okay, since f is homomorphism, so from G to G dash, then what is f of E is what? E dash. So this is the definition. So we have to prove that. Okay. So f of E is equal to E dash, where E belongs to H and E dash belongs to f of H. So where E belongs to H and f of E dash belongs to, f of E belongs to H or E dash belongs to f of H. F of H. E dash belongs to f of H. Okay? F of H. Okay. Now let f of A, f of B are the elements from the set f of H. So that is the image of H. So we are taking here the elements f of A and f of B. Then f of A into f of B inverse. F of B inverse. Then what happen here? So that is f of A. So f of B its inverse. This can be written as f of B inverse by theorem. By theorem. F of B inverse is equal to f of B inverse by theorem. So this is equal to f of AB inverse, since f is homomorphism. So f is a homomorphism. So this is very simple. Okay, now AB belongs to H. A and B are the elements of H. Since what is given here? H be a subgroup of G. Since H is a subgroup of G, then what implies? If AB belongs to H and H is a subgroup of G, then what happened? So this implies that AB inverse belongs to H. AB inverse belongs to H. H is a subgroup, then AB inverse belongs to H. So we studied already in the last lectures here. So this is very simple. So this implies that taking images of both, so that is f of H. So this is what happened here. So this can be written as f of A into f of B inverse, since function f is a homomorphism, belongs to f of H. Okay, f of H. So what happened here? So this implies that. So this can be written as f of A. So f of B inverse means what here? F of B in its inverse, so belongs to f of H. So if A B inverse belongs to G, or A into B, just see here, A B inverse belongs to H, then H is a subgroup. A B inverse belongs to H, then H is a subgroup. And if f of A into f of B inverse, then f of H is also subgroup. Hence, we prove that f of H is a subgroup of G dash. Hence, f of H is a subgroup of G dash. So proof is very simple here. Okay. So these are the theorems on homomorphism. So what is the next part? So what is the kernel of homomorphism? What is the definition of a kernel of homomorphism? Kernel of homomorphism. Okay. So what is the definition of kernel of homomorphism? Let f is a function from G to G dash be a homomorphism from G to G dash. Okay, the kernel of f is defined by kernel of f denoted by simply KER. So that is KER f. So that is the kernel of f, and is defined by So what is the definition of kernel of F? And is defined by, so that is the kernel of F is equal to, it is a set of all such elements x belongs to G such that fx is equal to E dash. Fx is equal to E dash. So what is the kernel of a function F? It is a set of all such elements. F is a function from G to G dash. And E dash is the identity element of G dash. E dash is the identity element of G dash. Then if fx is equal to E dash, then x belongs to G, then fx is equal to E dash, then the set of all such x is called kernel of F. So E dash is the element of G dash. And we find such element x such that fx is equal to E dash, identity element. Then such a set is called the kernel of F. Okay, where E dash is identity in G dash. Okay, E dash is an identity since function from G to G dash here. So what is the theorem here? So we see here the definition. So there is a big theorem. So we take theorem on a kernel of a homomorphism function here. Okay. So what is the theorem? If f is a function from G to G dash is homomorphism, then, so we write definition again here, then kernel of F is a normal subgroup, normal subgroup of G dash of G, subgroup of G. Okay, normal subgroup of G here. Okay, so what is the proof? Proof. So if f is a function from G to G dash is a homomorphism, okay, function, then prove that kernel f is a normal subgroup of G. So if G is a subgroup, G is a subgroup and H G is a group and H is a subgroup of G, then H is called a normal subgroup when? What is the condition? What is the definition? So that is G inverse XG. G inverse XG belongs to H. Then H is called normal subgroup. So we just revise the definition. Okay, H is a subgroup of G. Then the H is said to be normal subgroup if G inverse XG belongs to H. So we prove. So the theorem, and we have taken this many times. So it is not necessary to repeat again here. Okay. So what is the proof here? Okay. Let f is a function from G to G dash is a homomorphism. So that is given here. Then what is the, again we write definition. Then what is the kernel of f? Kernel of f is, it is a set of all such element x belongs to G where fx is equal to E dash. So E dash is the identity element of G dash. E dash is the identity element of G dash. Then, okay, since f is homomorphism, so that is given here, homomorphism. Then what happened? So f of E is what? F of E is E dash. So we also prove this theorem. F of E is equal to E dash. So E is the identity element of G and E dash is the identity element of G dash. When F is a homomorphism, then prove that this condition. So we prove this theorem here already. Okay. So F of E is equal to E dash. So here E is what? So what happened here? So Fx is equal to E dash. Then X is the element of kernel of F. Then F of E is equal to E dash. Then E dash is also, therefore E dash is the E is the element of kernel of F by definition. So Fx is equal to E dash, then X is the element of kernel of F. And if F of E is equal to E dash, then E is the element of kernel of F. Means kernel of F is a non-empty subset. Therefore, so that is first proof here. Kernel of F is a non-empty subset. Non-empty subset of G. Subset of G. Okay. So what is the next part here? So first we prove that kernel of F is a subgroup of G. Then we prove that kernel of F is a normal subgroup of G. First we prove that what? Kernel of F is subgroup of G. So what is required to prove that? So this is a subgroup of G, H is a subgroup of D. So simply we prove that AB inverse belongs to H. Then the H is a subgroup of G. And what is a normal subgroup? G inverse belongs to H. Then H is a normal subgroup. So first we prove that kernel of F is a subgroup of G. So let XY are the elements of kernel of F. XY are the elements of kernel of F. Okay, means implies that if XY are the elements of kernel of F, then what happens? So F of X is equal to E dash by definition. Also F of Y is equal to E dash by the definition. So this is very simple here. So consider. Okay. So what is F of XY inverse? We take F of XY inverse is equal to what? So F of X into F of Y inverse. Since F is a homomorphism. So by definition of homomorphism, F is homomorphic. Okay? Homomorphism. So this is very simple here. So what is Fx? Fx is what? Fx is what? E dash. Okay? So just we write this here. Fx. So what is F of Y inverse? So this is F of Y. It is inverse. So this is implied by theorem. So this is equal to, what is F of X? Is E dash. What is F of Y? E dash. It's inverse. So E dash is its inverse is E dash. E dash into E dash is E dash because E dash is identity element. And if F of, so this implies that F of XY inverse is equal to E dash. Is equal to E dash. Then what it implies? So this by definition, kernel of U. So this implies that XY inverse belongs to kernel of U. XY, this implies that by definition, this implies that XY inverse belongs to kernel of U. Therefore, kernel of F is a subgroup of G. Subgroup of G. So that is the first part is proving here. So kernel of F is a subgroup of G. So what is the next part? Prove that kernel of F is a subgroup of G. Is a normal subgroup. Normal subgroup of G. Subgroup of G. So that is proving here. Okay. So now let G be the element of G, small g. Okay. And X is an element of kernel of F, then what happened? Then f of g inverse xg is equal to f of g inverse xg is equal to. So this can be written as f of g inverse into f of xg. So this can be written as by f is a homomorphism. Since f is a homomorphism, so again we write by, since f is a homomorphism, then again we write this f of g inverse into fx into f of g. Okay? So then this equal to, okay? So this equal to, so what is fx? Fx is what? E. Fx is E dash. So f of g inverse, so fx is what? E dash. Because x is the element of kernel of f. X is the element of kernel of f. So fx is equal to E dash into f of g. So this into this. This into identity element is same here. F of g inverse into f of g. Since f is a homomorphism, so this can be written as f of g inverse into g. So this is what? F of g inverse into g. So what is this? G inverse into g is identity element. So that is E. But f of E is what? E dash. F of E is equal to what? E dash. So f of g inverse xg is equal to E dash by definition of kernel of f. So this implies that, what is the definition? If this is equal to E dash, if x is equal to E dash, then x is the element of kernel of f. Then if this is E dash, therefore g inverse xg is an element of kernel of f. Hence, so what is the definition? What is the definition of a normal subgroup? So this is the definition of normal subgroup. Therefore, kernel of f is a normal subgroup of G. So this is a very simple proof of this theorem. First we prove the kernel of f is a subgroup, and then we prove that the kernel of f is a normal subgroup. Okay, so we take examples on kernel of homomorphism to the next lecture. Thank you.